If you always wanted to learn about low-level JavaScript performance optimizations and best practices, because those are directly related to the engine underneath as well as the C++ code, then you are at the right place at the right time. Because in this video, we're gonna go over all of these interesting points because they are becoming very important whenever we're dealing with large chunks of data, because we wanna squeeze the maximum out of our JavaScript code, right? And with that said, I'm pretty sure you're gonna enjoy this video, and if you haven't subscribed yet, just make sure to subscribe because I'm publishing this kind of interesting videos. Sometimes it's more fun, sometimes it's more theoretical and practical like this one. And with that said, let's get started. Alrighty, so we're gonna start with the very first point, which is string comparison. And notice that I put everything in different folders. So every folder has a bad anti-pattern and the good one, the one that you wanna go for. So talking about string comparison, I'm gonna open this and just don't look at this code for now. Just let's focus on this one, okay? So in JavaScript, it's very easy to compare strings. We're simply using double or triple equals and they're being compared. Under the hood, it's obviously C++ code. I believe there's a function called cprstr, which does the comparison. But essentially what's gonna happen is every letter is going to be scanned. So the first letter of the first string is going to be compared to the first letter of the second string, and so on until we reach this character, and we're going to compare it with the index of the second string and see that these characters are different. And this is basically how string comparison is working. So letter by letter, one by one, comparing each character. Now, there are also use cases. Well, first of all, let me tell you that this is slow, okay? String comparison is slow, and whenever you can try, avoid it. Now, I'm gonna explain you why this is slow. So let's look at this example. We have an object called position, and I'm gonna delete this actually. This example, we don't need this anymore. And I'm going to open the good one as well, and I'm going to split the good one on the right quickly. All right, so we're looking at this example. So this is our enum, and what we're gonna do is we're gonna iterate a lot of times, and every time we iterate, we're simply going to compare the current basically element, which is either top or bottom, with the position top, okay? And every time it's top, we increment it by one, this variable. Okay, so the issue is here. Here we're comparing strings. Now, in this enum, we're gonna be comparing current, which is one of these, with whether it's top or not. And the issue with comparing strings in JavaScript is not only the fact that we have to go letter by letter, so T is going to be compared with B, O is going to be compared by O, and so on, but it's actually accessing the memory. So every time JavaScript runs, we're going to be storing all the variables in the heap memory, basically the memory of the JavaScript execution, so to say. So strings, arrays, object, booleans are all going to be stored in this yellow box memory. And just imagine that in this memory, we for now have just 4 strings: top, bottom, apple, and Friday, unrelated, right? So every time our code is being executed and we reach this if statement, what's gonna happen is we are going to reach out to the memory. So we're going to reach out whether this top or actually this current. We're going to grab the value of the current and we're going to grab the value of the top and then check if these are the same variables, because actually most of the engines are not going to compare string by string because they can see the whole file and see that, okay, we have 2 strings at this time, so let's put them already in the memory so that we know we have these strings and so that we don't have to go character by character. And now memory is being clever. It says that, okay, I already have these 4 strings in the memory. I'm simply going to reach out to my memory to see if this string is the same one that I'm referring to. And if the current is living at the same point as the top, position top, like this one, then the engine is going to say, okay, we're actually referring to the same point in the memory, and actually I don't need to go character by character anymore, and this is going to be true, okay? Now, The real issue is the fact that we are reaching out to the memory. The fact that we reach out to memory actually is the thing that slows down our application. Just remember that reaching out to the memory is always slow. And just to prove you that, I have this jsbench.me website open, which is going to run your piece of code that you put here in the cloud, and you can actually add one or more test cases. In this case, I'm going to compare the first one with the second one. In the second one, so in the bad one, we're going to be comparing strings to strings, so we have top. And in the first one, we're simply going to be comparing numbers. Now, let me show you the results because I already ran them. And comparing strings is almost 60% slower than comparing numbers. So basically, if this would be a number, comparing 0 to 0 or 1 to 1 is basically 60% faster than comparing a string like top to bottom. Okay, the issue is strings are just like objects and arrays, are always saved in the memory, in the heap memory. Okay. On the other hand, numbers like 0 or 1 or I don't know, 1,000, as long as it's a small number and not a big integer. So as you know, in JavaScript, you have big int. As long as it's not a big int, it's going to be passed within the memory by value and not by a pointer. Okay, just like objects, as you know, objects are passed by reference. These strings are also going to be passed by reference and not by value. That's why, and whenever you can, or whenever you're using enums, just leave them out and don't declare like variable or string values for them. Just leave them out like this, and this is going to be much faster. Okay, so this is one example that you should keep in mind. And actually, I'm gonna post all the code on GitHub so you can run this yourself. But just remember that string comparison in JavaScript is slow, so go with numbers whenever you can. And obviously, in this example that we're running, we have 1,000,000 of iterations. That's why it's so obvious. That's why we can tell the difference. If you had only 10 objects here, then you actually wouldn't notice the difference. All right. This is what our video is all about. We're working with large data sets, and this is when the difference is going to be noticeable, not when you have 10 objects. Okay. So now let's go to the second point. Or maybe let me mention one more thing. I have it open here before we go to the second point. Or just read this. All JavaScript values are allocated on the heap accessed by pointers, no matter if they are objects, arrays, or strings or numbers, as I said, except for small integers. So small integers are the ones that I told you about, 0, 1, or up to 1,000, up to, actually it can be a big number, but as long as it's not a big int, you're good to go. All right. By the way, this video is based on RomGRK's amazing article, because we have all of these points described here. I'm just making a video to summarize it, so you can go and read it, and shout out to this guy for making such an amazing contribution to our JavaScript world. And now coming to our editor, we're gonna go to the second point, which is different shapes, all right? So let's open the good and bad cases. Let's close this, and we're going to split it to the right. Actually, let's just keep it like this. So the bad case. The bad cases are, or actually the good case. Let's start with the good case. So what are object shapes? So let's say we have many objects, let's say 5 objects. And as you can see, they have keys, A, B, C, D, E, and values, all right? In this case, it's 1, then it's underscore, underscore, and so on. Underscore is basically referring to 0, okay? Now, all these objects have the same shape. So the first one is always A, the second one is always B, and so on. And whenever we perform some kind of a big operation on those, let's say we're going to have a big loop, and every time we're going to run this add function, and add function is going to accept A1, which is the first object, and B1, which is the second object. This is what we're passing here. We're going to pass the first object, second object, then the third, fourth, and so on. Now, what this point is about is that you have to try to make sure that your objects have the same shape, meaning that they're monomorphic, all right? Because apparently, every time you create a new object, let's say O5 is going to have a different shape, like B is going to be on the first place and A is going to be on the second place. This is a very small difference, and often when we write code, we actually don't care about this, saying that, okay, I mean, objects in JavaScript are just dictionaries. The position doesn't matter. It's not an index like an array. So I'm just going to put A at the second property instead of B being the second. And now every time we run this code, we're going to notice that if we go to the benchmark, we're going to notice that this is the fastest one because it's monomorphic. All objects are the same shape. Now going back to the code, we're going to look at the bad cases. A polymorphic case, which is, as I said, A and B are swapped their indexes or places, all right? A very small change, and it's going to result in a 10% slower code, okay? 10% slower code, I'm pretty sure you don't want that. And now let's look at the even worse case, which is a megamorphic. Megamorphic means that every object in our case is basically going to have a different shape. So megamorphic is almost 45% slower than a monomorphic object. What I'm trying to say is that every time you pass an object into your function, all right, make sure that all these objects have the same shape, like in the good case, or at least try to pre-process them and make them the same shape. Maybe let's say you are fetching some data from the backend and you have to do this addition on the front end. Make sure that the data that's coming from your backend is already sorted. Okay, it's much faster to process on the backend. That's why I'm saying that. But basically, you get the point. Make sure that your objects are monomorphic most of the times. Okay. All right. Now let's go to our third point, which is array object methods. So let's see what we have here. All of us are familiar with maps and reduce, and all these good functional code. Okay, in this case, we have a map, we have a filter, we have a reduce, and we're looping quite a lot of time. And we're basically creating a long array with random numbers. Now, everybody likes this, okay? But let me tell you something. Maybe you will not like this. Maybe you will not like what you hear now, but this code is really bad. Okay, this code is really bad if you want to be performant. If you have just 10 items here, like this, then you're good to go. Okay, you can do whatever functional programming you want, but unfortunately, we're in JavaScript. We're not in Haskell. We're not in Rust. So all this code is going to be not performant. It's not compiling directly into the machine code. So functional programming in JavaScript is very slow. Instead, what you can do is have a good old for loop and simply create the number here. And if basically this is the same thing as the filter, okay? You can do the filtering here and increment this result by n instead of doing a reduce. A very simple point, all right? But let's look at the benchmarks. Guys, this is 38% slower. So functional programming is usually 38% slower, or at least this case, than having a normal for loop. So always, whenever you're trying to optimize your code or dealing with large amounts of data, go with a normal for loop, all right? And just keep in mind that object values, object keys, object entries are also going to have the same impact. Now, let me explain why. First of all, it's obvious that we're mapping through the same array 3 times. So basically, if we have 10,000 items, this is going to be looped like through 30,000 times. Why? If we can just loop only 1 time over it, okay? This is very obvious. But the second thing is that, maybe this is not that obvious. Every time we make a map or filter or any of these functions on the numbers array, JavaScript is going to create a copy of this numbers array in the memory so that all these operations can first be performed and then merged into the numbers array, because we're not immutable. In this case, the result is mutable, right? But in this case, we're immutable, meaning we have to create a copy of it, okay? So creating a copy 3 times and looping over the same thing 3 times is never a good idea when you want to be fast, okay? Keep this in mind. And now we go to the next point, which is object access. So as you know, there are different ways of accessing objects. You can access it by brackets and the name, or you can just access with a dot. Okay, all good. But what I want to say is simply try to make your objects smaller or not that deep whenever you're trying to perform large operations on it. Okay, let's look at the bad case. We're looping 10,000 times, 100,000 times, and we have these objects A and B, and they have a state, center point, X and Y. So quite a deep object. Okay, and every time we're going to get either object A or B, and we're going to get the X point. All right, and the good use case is that we already have the X point of these, and our objects are not that deep, first of all. Okay, so having deep nested objects is going to cause your slowdown in your performance. So maybe try to break these objects down, change the logic in your app, because if you look at the benchmark, this is going to be 12% slower than having normal objects. Okay, maybe trivial, but just good to keep in mind that accessing objects, and the deeper you go, the slower your app is going to be. Okay, next point is cache misses. All right, so JavaScript is having a cache in the memory. Let's look at it. So actually, we already talked about this. These are about the object shapes. And just since I missed this, what this array of objects is going to compile into in the machine code after JavaScript is executed is we're going to have something like TypeScript does, like name and type string and type integer, and then they're going to be put into an action array. And because arrays are going to be faster, and Anthony is going to be 36 within the same array, the string and integer. Okay, now we're talking about, sorry for switching topics, now we're talking about cache misses. Okay, so what about cache misses? Cache misses are interesting. So it turns out every time we store something in the memory, so let's say here we're creating points, all right? We're creating points, a new array, which is going to actually result in a lot of undefined values in a big array. And what we're gonna do is we're gonna get the length of these points and override them as an object. So at the end, we're gonna have a lot of objects within this big array. Okay. The cool thing is that this code is fast because we generated these points array and already allocated memory for them in a normal way. We used new array. So let's say this whole array here, 1, 2, 3, 4, 5, is going to be located sequentially. It's not like this 2 is going to be somewhere far in the memory. No, they're actually going to be like next to each other. And every time JavaScript looks for a value, let's say we want to fetch the first 0 index of this array, it's going to look here. And at the same time, the V8 engine is, or also SpiderMonkey, other browser engines, they're smart. They're not only going to fetch your value that you're interested in, but they're also going to fetch some adjacent values from the memory, meaning probably 2 and 3 and 4 are going to be there as well, because they know that, okay, you're in a loop, so I'm going to fetch these 2 so that I'm faster. Okay, now the problem becomes, or starts, if we look at the bad example, when you shuffle the array. Okay, so here it's the same, we create the points, but now we're shuffling the array. So basically a misplaced array like this, and every time we look for the 2, maybe 2 is here at the old place, but now 5, it's got shuffled. 5 is gonna be somewhere else. And if we fetch 2 and our V8 engine tries to get the adjacent values, it's most likely not going to be there. So it's going to be a cache miss. We don't want to have cache misses. That's why make sure that you don't shuffle your array a lot. And basically, this is the gist of this point. Now let's go further and talk about some further improvements that we can do. All right. I'm going to uncomment this. If you want to go even further and optimize your code so much, maybe you have some mission critical code. Maybe you're sending some robots to Mars or some other planets, and you really care about every single byte in your memory. You can actually convert this data, which is XY points as objects inside the array. you can turn them, first of all, into a signed array, not a normal array, but a signed array, making sure that it's int64 or something else, and actually just putting them inside one array. As you know that you have only x and y, you can somehow deduct the fact that the first and second is gonna belong to the first array, second or object, third and fourth is gonna belong to this array. So again, object. So if you want to grab something from this array, you're gonna grab pairs. All right. I hope this is understandable. Basically, try to be very specific and try to avoid basically messing with your memory like this, because this is not performant. Okay, immutability. I just put this here to mention it again. Immutability is also related to the previous point that we talked about in functional programming. Immutability is good because it reduces the risk of overriding the value. As you know, that's why functional programmers like this map and reduce functions, because it creates a new array. But as I said, it creates a copy and it's low. So sometimes immutability or mutability is better. And also try to avoid this spread operator, because every time you do spread operator, it again creates a copy. So again, immutable, but kind of slow. All right. So we're going to go to the next point. Let me close this. And actually, we didn't look at the benchmark. Did we look at the benchmark? No, we didn't. So here's the benchmark. So as you can see, the points created in sequence are fast and shuffled points are 83% slower. This is terrible, guys. Just make sure that you don't have cache misses. All right. Whenever JavaScript accesses the memory, it has to be fast. Okay. So next point is gonna be large objects. Let's talk about this. So let's say we have an object and we have a user's length of 1000, and we're basically going to have a for each. So for each from an array, this is filling the object with data. So basically by ID is going to have 1000 entries by ID and name John. Okay, just stupid. But here's the key. Okay, we're going to then do another for each. And whenever you do for each by object keys is basically going to return you the keys of the object. And then you can get the original object and use the ID, because this is the key, to basically get the value. This is not good. Compared to the good case, let me put this on the right like this. The good case looks like this. Instead of doing object keys and then additionally referencing it like this, you can already do object.values. Object.values is much faster because it's automatically going to get a value of the key of the object. And just like this, you can just access the ID of the user. Okay. So object keys versus object values. Whenever you can use object values, especially with big objects or large objects, as our folder is called, make sure that you don't do unnecessary accessing of the object keys. Okay. And let's look at the benchmark. We're going to see that this is 12% slower. So this code is definitely fast. Okay. All right. Now let's close this and go to the next point, which is string mutations. Very straightforward example, but apparently string mutations are no bueno. So let's look at our class names. We have some class names, and what we're doing is a good old map. And since we don't have that many objects, in this case, I'm saying that map is fine. Okay. What we're going to do is we're going to join these class names into one long string. Okay. So far, so good, but apparently not that good, because looking at the good example, what instead we have is just the good old plus sign and space. Okay. This looks kind of old, like from the old century. This is kind of ES6 because we're using backticks and so on. But guys, this is much faster, because every time we do string manipulations like replace, trim, or join, we create an additional copy of this string. Okay, we create a copy, and if you especially do it inside a map, it's going to result in many copies. All right, so 4 copies at least. We don't want to have copies because those are going to be living in the memory somewhere. And as you know, we need to keep the memory as slim as possible. On the other hand, doing pluses is simply, in this case, every time we do ec plus c, we're simply going to have a pointer to this class names array, and it's not creating any copy, but rather already accessing the data that it has in the memory. So the good old plus is always faster. Let's look at the benchmark. And as you can see, joining, meaning string mutations, are 60% slower. Okay, this is quite bad. And it's already doing it. It's already performing so bad with just 4 items. Just be careful, okay? Maybe save this video to watch it every day until you are very familiar with all these concepts, okay? Now, point 8, specialization. Now I managed to pronounce it. Let's look at the bad example. Let's say we have some e-commerce shop. We have some descriptions of apples, bananas, and basically these are tags. What we can do every time we try to loop and turn the product names to strings is that we can have a loop. So we're doing description for each, and then we can check if the text already has the product, then we're simply going to add it. Okay. Now, the trick is that we're not really specializing the code to our business needs, because the case is that no text is mostly going to be empty, as it is in this case. Okay. So why do this if check inside the for each if we know that the text is mostly going to be empty? Sorry, some text and no text. Okay. In the good case, though, we are specializing our code to our business needs. What we're going to do is we're already, before doing any loops, we're going to have this is empty object or function that's going to check if the object is empty or not. If it's not empty, or rather if it's empty, then we're going to do something similar that we saw in the other example, but of course without the if case now. So this loop is going to be much faster. In the other case, okay, we're going to do our good old function that we did, and of course have this ugly if statement again. Now you can see that this resulted in more code because we have 2 branches, this branch and this branch. But if you're trying to optimize your code and you know that you have too many iterations, not 100, but maybe even tens of thousands, it's better to quit earlier. So as you know, it's good to quit the functions earlier. So this is kind of a way of signifying that if I know that this is a special case, we specialize in it, then we're going to have a slimmer function. Okay, I hope this makes sense, because otherwise, if we go look at the benchmark, we're going to see that obviously this is slower because we do some additional operations inside our for loop, and we usually don't want that. Okay, the last point is data structures. As you know, you've probably already done some lead code challenges and studied data structures at the university or school, but I'm just going to repeat it again. Okay, let's look at this code. Eventually what we're doing here is we're checking if admin IDs array includes some kind of an admin ID. Okay, includes is okay-ish, but it's slow. Okay, because includes because there's a better way to do that now with ES6, which is the native sets or maps. In this case, we're going to actually create a set, and the set already has this has method. Has is going to return a boolean indicating whether an element with a specified value exists in the set or not. So why not use has instead of doing an include? Okay, so has is going to be always faster. And let's talk about this for a second. Okay, so I'm gonna link this page so that you can read like the speed of JavaScript collections, set versus map versus array versus object and so on. So it's kind of a nice article, but just this sentence that I want to show you. So memory usage. Set tends to use more memory usage than array because it needs to store additional information to maintain the hash table. However, the difference is usually negligible for small collections. Speed. Set is generally faster than array for operations that involve checking the presence of an element, such as has or add. Okay, so set is already optimized for checking has or add. So whenever you're doing that, make sure that you use has, because it's going to result in a constant time, while checking if an array has an element or not is going to result in O and N, because it has to go through the whole array. Okay, so far so good. Now, one more thing, maybe also interesting for you. Try to not use arrays all the time. Maybe there's a use case for a linked list. Okay, if you have an array like this and you have 1,000 items, you have to store all of that in the memory. And every time one item changes, or you remove, let's say, one item by array.pop, okay, it's going to remove one, not prototype, but pop, as you know, or shift, it's going to remove the element from the beginning. You are actually going to reindex the array on the fly, and this is slow. Okay, instead, you can do, first of all, set, as we said, but also you can simply use a linked list. Linked lists are very nice. Okay, linked list is basically this: every element is going to point to the next element, and there's no reindexing, because there's no, it's not an array. Every time you push something, the array doesn't have to be reindexed. You just need to point the last element to this new element. If you delete something from the middle, you need to make sure that the previous element now points to the next element. You probably know all of that, so don't have to repeat, but just let's repeat the points why you need to use it, so you don't have to worry about reindexing. It's more efficient for inserting elements as well as removing, and it's great. It's a great data type for queuing, especially first in, first out. Okay. Now, guys, if you like this video and you haven't subscribed yet, please make sure that you do. I'm going to be publishing more videos like this, and I'm going to create a course on cloud computing or best practices of cloud architecture and so on. I haven't come up with a name yet, but basically, please support this video and go check out the original article of ROM, because it's just precious. All right, guys, and I will see you in the next video. Goodbye.